Hello, in this video we are going to see an introduction to indifferent curves and budget constraints. Okay, in the previous video we have seen supply curve in microeconomy, and this concept is useful to understand this graph, which is the supply curve in the medium run analysis in macroeconomy. In addition, these two graphs use the concept of indifferent curves and budget constraints. If we amplify this figure, then we get this. This graph represents the strategy that the central bank used to target inflation and also GDP, real GDP per capita. So this is this graph, and this one is the three-dimensional version of this graph. So in future video we are going to see these two graphs with much more detail. Let's see it bigger. And what we are going to see in this video is the concept of indifferent curves and budget constraint, but not in this medium run analysis, because to understand that we need Phillips curves and other labor market. So now we are going to explain this concept using a much simpler example. So in this video we are going to use this surface instead of this surface, and we are going to use this plane, which represents the constraint, instead of this plane. And if you see this picture from above, then you will see this, and if you take a picture of the base of this parallelepiped, then you will get this. So with this example it's going to be easier to understand indifferent curve and budget constraint, and then once we learn with this example this concept, then we apply for this macroeconomical case. Okay, so the problem that we want to solve in this example is to find a point here in 2 dimension within this magenta line that represent the constraint that maximize this utility function. And in this video we are going to see that this point turns out to be this point here, phi and phi. So this is what we are going to see in this video. Okay, let's take a concrete example to explain indifferent curves and budget constraint. Okay, let's suppose that we want to print label. In Spanish is etiquetas. And these labels are printed in a company that uses printers and cutters. So in the first stage you get the printing according to the design, and then in the second stage you get the labels. And let's assume that the demand for label is going to increase a lot, so this company want to buy more printer and more cutter, and let's assume that the price of one printer is $1 million and the same for the cutter, and this company has a budget of 10 million. So the quantity of printer that we buy plus the quantity of cutter has to be 10. In general you have quantity of printer times price of printer plus time of cutter times price of cutter. But in this simple case both have the same price. And let's assume that the utility that you get if you buy this quantity of printer and this quantity of cutter is this. In the next video we're going to show why the graph for this utility function is this. So the problem that we want to solve here is to maximize the utility but subjected to this budget constraint. So if you represent the budget constraint in 2 dimensions, you get this, because if with 10 million you buy only printer, then you will buy 10 printer and 0 cutter. If you buy only cutter that costs 1 million and no printer, then you will get 0 printer and 10 cutter. and all of the solution lies in this line, in this magenta line. For example, here you have 5 printer and 5 cutter, and 5 plus 5 is 10. If you want to see this in 3 dimensions, then this is the case you buy only printer, this is the case if you buy only cutter, and then you have this line that if you see in 3 dimensions, this is going to be a plane. And if you see this from above, then you will get something like that. And if we take only the base, then we get this, and then we are going to take a picture of the base of this parallelepiped, and then you get this, which is very similar to this. Well, the point within this magenta line that maximizes this function is this point. That if we see in this graph is this point, and 5 printers and 5 cutter is the solution that fulfill the budget constraint and also maximize the utility function. So how we can find this optimum? Well, first let's see a graphical solution. First thing, if you evaluate the function in this point, then the utility value is this value, which is 10, which is this 10 that you have here. Now, all of the points that are here, okay, that here is this, has this level 9, or here has this level 9, mean that in all of these points the function evaluates to the same value, which is 9, lower than 10. Now if you go on going down, now you go like this, you go like this, so in all of these points then you have here 8, level 8, meaning that in all of these points the height is the same, is 8. In all of these points the height is 8. So these are what is called indifferent curves, because respect to the objective function, the utility in this case, it is indifferent to take this point, or this point. All of them are going to evaluate to the same value, 8 in this case. The graphical solution is to find an indifferent curve that is tangent to this magenta line. The utility for the optimum is 2.5, which corresponds to this yellow curve, which is between 2 and 3. So it's actually 2.5. So this is the graphic way to find the optimum. Okay, in the next video we are going to see how you can find this optimum analytically. Okay, thanks for watching and see you in the next video.